And this is some of the results we can expect. Now, none of these are multi-lumen tubing, single lumen, but we can look at these and kind of apply forward some of the things we see. So this is a polyethylene tube. You see the quality of the features, the edge quality of the features machined there. This is a polyimide tube that wouldn't come into play in cardiac pacing lead bodies, but here you see the different angles of attack that are very easy to achieve with laser machining. We're basically loading a piece into a chuck and we're rotating it with programmable motion. And so we're getting, you can imagine, a feature in one lumen, rotating it and getting a separate feature in an adjacent lumen. Here, this is silicone tubing. And so you see in the silicone tubing, which is applicable to pacing leads, very small, precise features. The features are repeatable. The spacing of the features is well controlled through programmable motion. Let's check my notes. One thing that kind of a watch out or a concern here is that we do use some tooling in the form of mandrels to serve as beam stops. So we'll load the tubing, the catheter, or the lead body, in this case, with a beam stop, typically a ceramic mandrel, sometimes a stainless steel mandrel or a coated stainless steel mandrel, so that our laser energy doesn't compromise the tube wall and affect the adjacent lumen. Those tools, those mandrels do wear with time, and so the process does require monitoring of that tooling. Something I'll mention here just briefly is that if we're machining silicone, pure silicone, it's actually not a photochemical process, it's a photothermal process that goes through two phase changes before the material is evacuated. It can leave debris. There can be post or secondary op cleaning required, but with the polyurethane and the silicone polyurethane Persil material, it's a clean process, does not require any secondary operation for cleaning. Some additional features that this type of machining can give us, we can very quickly, with a remask and a reprogram, we can really quickly explore some different texturing, some different patterning, and this can be helpful for designers of catheter leads if they're looking to enhance flexibility or fixation in the distal region of their lead. Next, we look at the lead cable. The function here is very basically to transmit signal back and forth between the pulse generator, the sensing pacing electrodes, the shocking coil. The conductive material is going to be a cabled or a stranded, very fine MP35N, MP35NLT conductor. Can be somewhat delicate, that conductor. The insulation of this lead cable is typically a fluoropolymer. ETFE is the type of fluoropolymer that's typically used, a type of Teflon. And that's really what we're going to focus on in this conversation, is the removal of that insulation. And the goal, why remove the insulation? To create a clear path to contact, to attach the electrode, the termination to the conductor. I mentioned crimping here. Crimping is a common method of attaching an electrode, a termination to these conductors. Again, much like skiving, it's a very intuitive, simple, available process, successful. The process can't work well unless we're doing our job of removing the insulation material from the conductor. Crimping a key component like an electrode to the conductor through insulation is really not all that viable. And so methods need to be employed to remove the insulation. Laser machining is really one of the best methods because it's non-contact. It's not going to endanger or damage the conductor, and it's going to give a very repeatable, stable precise landing zone or ablation area that can match perfectly to the width or length of any electrode or termination component. And so here we see this vaporization process, which is the same kind of process I alluded to when I mentioned the machining of silicone. Why is this different than the ablating process we saw earlier? The material, the fluoropolymer, the Teflon, has an absorption band that's in the infrared spectrum, so it's about 10 microns as opposed to in the hundreds of nanometers. And so we're using typically CO2 infrared laser energy to interact with this material. It's a thermal process, it's a photothermal process, and you can see as the illustration sequences, you gotta be careful not to shoot the guy across the hall in the eye with this thing. So laser energy is applied. There's a thermal conduction, a thermal reaction. We've got a liquid interface, so the phase change goes first from solid to liquid, and then it gets vaporized and ejected and changes to gas. So we have this interim state, and you can see kind of the edge quality or the wall or the aspect ratio is quite different because we've got heat spreading across the surface as the laser energy works down through the material. Okay. This actually isn't an example of a laser ablated cable, but again, it illustrates a point that I want to talk about, a couple points. So these are the watchouts when we're doing laser. If we're putting too much heat in, this transition from insulation to conductor can get a little sloppy. Not cut like this. This is obviously a mechanical wire stripping process, but we can get some melting or some rollback here. If we're putting just way too much heat into this conductor, we can get a heat effect zone. That would be real sloppy processing. It's hardly ever seen. We can get a redepositing as this melted material then turns to gas. Some of it might coalesce and redeposit as what we call a stringer, a small particulate of the Teflon onto the conductor. And then the big concern universally, when you remove the insulative casing of this wire, of this cable, you're going to see some fraying of the conductor. So those are the watchouts, and here's what it can look like if we're doing our job right. We're having a very clean exposed conductor. It's non-contact, and this is very delicate stuff. This is really a cable for a different application, but this is the kind of cable that's used in the pacing leads. And so by scale, you can see how delicate this is. The cable's undisturbed. The edge quality, very clean, very straight. We're not seeing the melting or the blowback. And to combat that fraying problem, we can hit the end of that cable with a little bit of laser energy, a different kind of laser energy, with a YAG welder, 1 micron wavelength, and we can put a little ball weld on the end that's going to encase or encapsulate that stranded cable and also help facilitate insertion of this cable into the multi-lumen tube body. Additional features, maybe a real icing on the cake, maybe the cherry on top, beyond just the core demand of what's needed here. This ETFE Teflon is very easy to mark with laser energy, and so we can come back in and mark the different cables. If we got 3 cables in a multi-lumen lead body, and under microscope there's an assembly operation going on, and we want to be clear that we're putting cable 1 into lumen 1, we can come back and mark each one of those cables. We developed this kind of a Morse code system for one of our customers, and they really benefit from this. Moving on to the lead label. This is an example of, or a few examples of laser marked lead labels. The function of the lead label is fundamentally to identify the lead with a unique identifier, whether that's a barcode, 2D barcode, serial number. We're going to put part number, lead length, manufacturer's name on there, maybe an opportunity for branding. And there's the goal here is to basically achieve the most distinct mark possible for the lead label. This is commonly going to be overmolded after it's assembled onto the lead. We want very distinct, easily legible marking, and we want this to be easily assembled. Competing methods, pre-printed labels are a strong option, a traditional option that laser marking is starting to replace. This image gives you an idea of the challenges that pre-printed labels are going to face. You're trying to apply a flat label onto a very delicate cylindrical object, which often involves a lot of human factors in manufacturing. So this is typically a manual process. There's a fair amount of rework to get that label positioned just so. And what we can appreciate is that if we get things maybe just a little cockeyed, a little crooked, that can serve to undermine confidence in the device. So we've got this fantastic life-saving device, and the label on that thing looks a little crooked, hard to read. Think of a Rolls Royce or a Bentley where the hood ornament is a little bit won't stand up straight, or the badge emblem on the hood of your Mercedes is faded from the sun and you can't even really see it. It compromises the confidence and the quality or the perception of the device or of the vehicle. One thing that pre-printed labels really has in its favor is the introduction of color. So with pre-printed labels, a printing process, you can do a vibrant blue for an OEM logo, a red that really stands out to alert someone to a safety or a hazardous concern. And color is not possible with laser marking. To revisit this type of slide, we're back to our photochemical slide, this time in marking. And what's great here is that we're typically marking silicone tubing. Silicone has a very high band gap. It's not going to change phases unless you put a fair amount of energy into it. And so we're doing all of our marking within the solid phase. We're really doing all of our marking right here. We're using near UV, 355 nanometer typically. And that wavelength is associated with relatively low energy levels. So we're able to put energy in to the tube without, that's well below the threshold that's going to change this from solid to gas or solid to liquid. And what we're interacting with our laser energy is a doping medium in the material. You notice the example I showed you earlier was a white label. There's titanium dioxide required for this to be achieved. But what we're able to do is, with laser energy, we're able to get in there and modify the titanium dioxide without modifying the bulk characteristics of the silicone tubing. And here are the type of results that we can achieve. Again, that first example I showed on lead label slide was also laser marking. But here we can do obviously branding, logos. We can mark 360 degrees of this cylindrical object, so we can do 3, sometimes 4 lines of text. We can change fonts within a single line of text. We can do the 2D barcodes, and we can create live barcodes in very, very small, decreasingly size formats. So as leads get smaller and smaller, we can embed them with all the data that's needed for traceability. That data is available through automated data capture. And we've got examples that our people can show you of extremely small 2D barcodes that are live. And so that really opens up possibilities here. Let's see. I think I might need to... Sorry that I'm kind of stumbling. Yeah, the watchouts are, the drawbacks are that it will require titanium dioxide. That will make the component opaque. And some lead manufacturers in assembly like this component to be somewhat translucent so they can see how parts are being assembled underneath the label. A great advantage here is that we can laser mark existing components of the lead. So if there's a strain relief boot, a formed silicone boot as part of the lead assembly, and there always is, we can mark that boot, turning a boot into a label. That allows us to reduce bill of materials, eliminate manufacturing steps for our customers. And so applying the boots to the lead is already an existing process step. They would essentially eliminate the need to attach or adhere a label. If they are going to adhere this label, it'll slide. It can be expanded. The silicone can be expanded and slid very neatly up against a hard stop onto the lead body, so you're not going to have any crookedness. And so the laser marking is really going to support that brand or the integrity of that product. Nothing about laser marking says poor workmanship. Everything about laser marking says this is a high quality operation. So we're coming close to wrapping up. I'll restate the challenge. The challenge is to improve upon the situation we see here, to make leads easier to implant by consolidating function, multiple functions. What used to have to require 3 leads can now happen in 1 lead. It's to make leads last longer, live longer, and it's to make this whole endeavor easier to manufacture. So to summarize, how does laser machining stack up? What are the benefits? Well, with the photochemical ablation of this silicone polyurethane blend lead body, we can achieve all those great effects of photochemical ablation, real great edge quality in these lead bodies, these multi-lumen lead bodies. We can facilitate the consolidation of function in a single lead. We can go ever smaller and smaller. Our laser marking, again, can reduce the bill of materials. If we're marking existing components, it can reduce manufacturing steps. Being able to work so well with that new silicone polyurethane blended material is the key to achieving a 20 or 25-year lifespan for cardiac pacing leads. The precision of laser machining really opens up the opportunity that cardiac pacing leads, their manufacturing could be automated to eliminate the human factors, almost like a pick and place. If you've got components that are perfectly married and can seat well to each other, pick and place, hit it with a crimp tool, hit it with a laser to weld the components together. So we're reducing yield loss, we're increasing cycle time and throughput, and hopefully helping our customers achieve their goals. That's the end of the presentation. I thank you for your time. If you'd like to have a conversation afterwards, we're at booth 1751. There's a few of my colleagues outside the booth. We'd be happy to talk to anyone that's got a question. This is a kind of a collage of the many different things we do, and it's all focused on catheters and implantable leads. Thank you for your time.